this is going to be the first lesson that we do in our new unit, and our new unit is on dynamics. And so, like I said, either write down notes or just watch, or watch me teach this again later when I post this onto YouTube. But here's the start of topic 2. And we're going to begin with a topic on forces. We're going to discuss forces. And I'm going to begin with some terminology. I'm going to discuss with you what dynamics means. Okay? Now, the basic idea behind dynamics is that it discusses the why as opposed to the what. Let me say that again. Dynamics tries to explain why things happened, not what they did. Kinematics is all about what happened, right? We just finished a unit where we tried to describe how far did it go, how long did it take, at what angle did it go, and it's all about what happened. Dynamics tries to explain why did it happen in the first place, right? Like as an example, why did the object fall? Why did I throw it? Like what caused an object to go into motion? Right? And that's what I have right here. Kinematics studies the motion of objects, but kinematics does not care about the cause of the motion. That's what we're going to discuss next is why did it move in the first place? Or why did it not move in the first place? Often it's because I didn't move it. Right? Like if I throw something, that's the cause. We're going to focus on that. Okay. Because he is so influential and so important, we've actually named this entire branch of physics after Sir Isaac Newton. They actually call it Newtonian mechanics. And like I said a little while ago, we're actually going to talk about Newton's 3 laws of motion over the next couple of classes. So we've named it after him. And it tries to describe not only projectiles, but also celestial bodies. Do you guys know what a celestial body is? Planets, comets, stars, suns, stuff like that. Yeah. Because really, here's how Earth's kind of history of physics kind of developed. Isaac Newton tries to discover, well, if I throw this, why does this move? And then they start to ask questions like, well, what other things are moving other than things on Earth? And they discover, hey, there's stars and planets up there. They seem to be moving too. Right? That's actually where the word planet came from. It's actually Greek from planetes, which I believe means wanderer. They actually recognized that planets were wandering across the sky. They knew they were in motion. And so scientists tried to figure out, well, why are they in motion? So we will talk about celestial bodies at some point. What we won't talk about yet is subatomic particles, because this is not part of Newtonian physics. But subatomic particles actually means we're talking about the quantum realm. And for those of you who watch superhero movies like Ant-Man and Avengers, any of you guys watch that stuff and they talk about quantum realm? Yeah. That's actually real. Not like the actual technology that makes you zoom down to that small, but there is such a thing as quantum. Like that, they're not just making up pretend words there. Quantum really refers to the microscopic level when you're talking about subatomic particles. So Newtonian physics then describes big everyday life stuff. You and me and the basketball I'm going to throw, even the moon, is considered Newtonian physics. But there's an entire branch of physics known as quantum physics, which is all about microscopic particles. Now, I need you guys to know 2 scientists and just a little bit of their contributions to history. And the first one we've already discussed. His name was Galileo Galilei. And I did a really basic experiment of that one white table before, where I think I dropped 2 objects, and they fell and hit the table at the exact same time. That's what Galileo did. The legend is that he went to the top of the Leaning Tower of Pisa. He took 2 cannonballs, one heavy, one light, and he dropped them. And everyone at the time subscribed to what Aristotle thought. I mean, he was Aristotle. He was supposed to be a pretty smart Greek philosopher. Aristotle thought that heavier objects fell faster. And Galileo kind of proved that's really not true. The mass of the object doesn't really affect how fast it goes because gravity pulls everything at the same rate. And so that was one of Galileo's biggest accomplishments. I've got a few more notes on here, actually. He also is known for his accomplishments with his telescope. He actually discovered mountains on the moon, spots on the sun. He discovered moons around Jupiter. And because of this is kind of a cool side note, he supported the heliocentric universe theory. You ever heard of that before? Heliocentric? You learn about it in grade 9 science, in case you've forgotten. So there were two competing models. One of the models was the Earth at the center of the universe, and everything goes around the Earth. And then the new model was the sun is at the center of our solar system, and everything goes around it. And up until that time, the Catholic Church believed that the Earth was in the middle. People are on Earth. People are important. I don't know what the rationale was exactly, but the Catholic Church believed the Earth has to be the center of the universe. Now, we know they're wrong, but both Galileo and this guy here, Nicholas Copernicus, they made a new theory that suggested that actually the sun, here's the sun, that's a horrible sun. The sun is at the center of the universe, and all of the planets go around the sun. That's known as the heliocentric universe. Anyway, it's kind of a cool side note story. Galileo was actually placed under house arrest. He was arrested for heresy, for basically disagreeing with the church. And he had to spend like the rest of his days basically locked up. And this is the funny part that I like about it here. They finally overturned his conviction. Pope John Paul II in 1992 decided to pardon Galileo. I just thought that was kind of ironic because Galileo lived in like the 16th century, 17th century. And it took 300 years for the Catholic Church to finally say, okay, Galileo, you're right. We apologize. Sorry for arresting you. You've been dead for 300 years, but... Okay, here's another guy I need you to know. He was a giant, not like actually a giant, but he was a giant in the physics world. Like Sir Isaac Newton was literally, he was Sir Isaac Newton. He was like considered to be the smartest scientist of his day. And here's one of the cool things about physics that's kind of crazy. He was born in the same year that Galileo died. And a lot of people think there's a lot of symmetry to that because Galileo was like one of the first big physicists to like come up with things. And as soon as he died, that was the year the next big guy was born. That's kind of cool. He attended Cambridge. He actually became the chair of Cambridge and discovered and founded calculus. And this is what we're going to focus on over the next couple of days. He has three main laws of motion that we're going to discuss one each day. Today's kind of my intro day. Tomorrow in the next few days, we're going to discuss a new law of motion that Newton described. And here's one more interesting fact about him. He had a intense rivalry with a guy named Robert Hooke. Like intense. Like they were enemies. They really were. Here's a kind of a cool side story. Back in like the 16th, 17th, 18th century, they didn't have cameras, right? But every famous physicist or chemist or scientist, there was always a portrait done of them for posterity so that we knew what they looked like in the future. So there's a portrait of Galileo. There's a portrait of Newton. There is no portrait of Robert Hooke. And one of the theories is that Newton, being a very vengeful and angry fellow, might have caused it to go missing when he was like chair at Cambridge because they had like a huge, huge rivalry, the two of them. So it's kind of funny to think of scientists like having like gangs and fighting each other, but anyways. And then the last one is I put down a note. He was actually knighted though. Like Sir Isaac Newton, although maybe a little vengeful to other scientists, he is Sir Isaac Newton because he made a lot of meaningful contributions. So we're going to discuss those over the next little while. Okay, so let's get back to dynamics now that we had our brief, some cool facts about some physicists. Why do things go into motion? What is the purpose? Like, why do things begin to move? And the word that we have to describe them is a force. And you've probably heard this word before. A force is known as a push or a pull. Right? If I were to throw something, that's a push. If I were to grab it in, it's a pull. You guys ever heard that maybe in Science 10? That's the definition of a force. It's not a very good definition, actually. It's what we start with, but here's a better definition. It means that an object's motion has been changed. That is a good definition of a force. It's something that causes an object to change. Right? If there's no forces, things don't move. We'd have a very boring universe if there were no forces. Everything would just sit there, like this. Okay, anyways, right? But if we have forces, we have changes in velocities. And if we have changes in velocities, it means there's acceleration. Here's what I'm trying to get at. If I ask you what physics principle we're talking about non-uniform motion. Because if we have uniform motion, nothing's changing. If you're always going the same speed, or if you're just sitting there, you have uniform motion. That's boring. Nothing's changing. So in order for there to be a force, there has to be non-uniform motion. Something must be changing. That's the definition of a force. Now, one of the things that we're going to do as a way of trying to communicate and visualize forces is a skill called making a free body diagram. And here's how a free body diagram works. What you do is you draw a picture of whatever it is that you're talking about. Here it's a car. And you just draw some arrows describing all the forces acting on it. And I found this picture online. I don't even know what all these forces are necessarily, because I actually don't even know what RR stands for. But I do know a few forces. You guys should know a few. Here, there's a force of gravity. Right? Isn't gravity a force that causes things to move? Or how about this, the force of the motor causing the car to move? Or how about the drag force that's trying to slow it down by providing resistance, aerodynamical resistance? Right? And so that's kind of how a free body diagram works, is that you draw arrows illustrating what's happening. So let's start with a really basic example here. Let's draw a free body diagram of a person standing still. I can't really draw a person all that well. Often what we'll do is we'll just draw a box, because boxes are easy to draw. So imagine that I'm just standing here. What forces are acting on me? Ah, well, we did know of one, yeah. Well, it means gravity. Well, gravity pulls me down, doesn't it? So let's write it as F with a little g, because the G stands for gravity. But hang on a sec here. If there was only one force, the force of gravity pulling me down, it means that I would be falling through the floor. It means that I would have broken through the floor, or I'd be getting squished downwards. But there must be other forces involved. And so there is actually another force involved. And it's going to be pulling upwards, and we write it as Fn. And the N stands for the word normal, and I have no idea why we picked the word normal. But there's something known as the normal force. Let me describe this to you. As I am standing here, gravity's trying to pull me down into the basement. What's preventing me from crashing through the floor? The floor. Doesn't the floor have some structural integrity to it? And the floor is kind of pushing me back up, if that makes sense. All right, now let's say that I wasn't, me. Let's say that I weighed, 5 tons. Well, maybe I would actually break through the floor because my gravitational amount breaks through the normal force. Imagine, again, you just have to hypothetically imagine, but imagine that I made a house of cards on the table here, right? And then I put my book on top of it. And the book caused the house of cards to collapse, right? Or a bridge that collapses. That usually happens because there's not enough normal force. Because normal force is the force of the ground. Well, I actually will draw a person here. The normal force is the force of the ground keeping the person on top of it. Otherwise, you just go crashing through the floor. So that's actually one of the first forces I want to describe. And then the other thing I want to point out is that in this free body diagram, see how this person is standing still? These two arrows right here should be the same size. Because what would happen if this vector arrow right here, what if the force of gravity was this big? Let's call it 100 newtons. Now let's say the normal force was only 90 newtons. What would happen? The floor would collapse, right? And you would break through the floor. So if a person is standing still, it means that both of these vector arrows should be the same size, and they should both be 100 newtons. So what's really cool is that the normal force is always the same amount as gravity if something is just sitting there. Yes? Question? Yeah, you'd be doubling the gravity. So, I mean, it does, yeah. Maybe think of it this way. The normal force will have a capacity, right? So let's say we stood on this desk, right? I stood on the desk, holds my weight. You and me stand on the desk, still holds my weight. But the table has to undergo more normal force to hold more of our weights, right? A third person stands on the table and it collapses. Well, at this point here, we must have hit the capacity of the normal force because eventually it's going to run out. Eventually, it doesn't have enough force. It can't handle that much force. Does that make sense? But it only provides as much as is needed for the force of gravity. What if the normal force was greater than gravity? You'd be floating. That doesn't really make sense. You get what I'm saying there? Because if somehow normal force was, say, 1,100 newtons, and this force right here was 1,000 newtons, well, then somehow you'd be getting pushed upwards somehow, and that's not how things work. Did that answer your question? Great question, by the way. Okay, I've got some slides here that kind of explain things, but I got to get to 2 examples here in the next 25 minutes, so I'm going to keep motoring on here. Normal force, then, is the force perpendicular to the surface, right? It is the force keeping the object from falling. Otherwise, we just keep falling for forever. Eventually, something has to rest on a surface, and the surface is pushing back up. And so the word we often use is net force. That's the phrase we use, net force, which is really like how much total force there is. Use this example right here. Let's say that somebody pushes a little bit this way, like say 10 newtons of force. But someone's much stronger. They push with 50 newtons of force the other way. Who wins in this big fight? Well, the person who pushes stronger, right? How much would the net force be? 40. How did I figure that out? I just subtracted them, right? Because really, this guy's 10 cancels off like 10 of this guy, and there's 40 left over. Often a great way of trying to illustrate in your mind the idea of forces is the picture I had on the very, very first slide we had in the whole unit. It's the picture of the tug of war. If you have someone pulling this way with, say, 100, and someone pulling this way with 120, well, now we know who's going to win, because 120 is bigger than 100. How much net force will there be? 20, because this guy has 20 more than that guy has. Right, the other thing that's on this slide that I want to point out here, let's go back here. On the slide I want to point out is that we often use a little subscript in the corner, like Fg is a way of keeping track of the force of gravity. Or Fa is maybe an applied force where I'm pushing something. Ff could be the force of friction. Ft could be the force due to tension in like a rope or a string or something. We just discussed Fn. We call that the normal force. It's the force of like the table or the ground holding you up. And the final one that we'll use is then the net force. And the little note we want to put on here is that the net force doesn't get drawn on the free body diagrams. The net force is what's left over when you're done, kind of like adding and subtracting. So let me do a couple more examples here to kind of illustrate this. The next few are just pictures. So here's a picture. Here's a picture of someone pushing a box. Let's talk about what forces we see in this picture. Right here, gravity. I mean, clearly the box is not floating above the surface of the ground, and gravity is pulling it down. But the box also didn't go crashing through the floor, which means that there must be an exact same amount of normal force, because the floor, right here, is kind of keeping the box from going through it, right? But you can imagine that if the box was heavy enough, the floor might have a hole go through it. But there's more forces. Right here I've drawn an applied force because it looks like this person is pushing. But I've also drawn, and this is Ff, by the way, for anybody who maybe has this printed off. This is a frictional force because as the person is trying to push the box, sometimes it's not easy to push things because friction prevents you from pushing. And so this would be a great example of what we call a free body diagram. Only we'd probably draw it more like this. We'd draw one arrow as Fa, another arrow as Fn, another arrow as Fg, and a third arrow as Ff. And it's just kind of a way for us to visually keep track of all the different things that are happening. Here's another picture. Here's a picture of, there's no question here. Here's another picture of a car, and I'm just talking about the forces involved. A car weighs 10,000 newtons. Okay, so that's its force of gravity, 10,000 newtons. But if it's experiencing a normal force, the normal force better also be 10,000 newtons. Why can't it be more or less? Why couldn't the normal force be 10,001 newtons? Say that again? Yeah, because if there was more normal force than gravitational force, it would start floating. And why can't it be a little bit less? Because then it would be like breaking into the ground. And so that does happen sometimes, by the way, though, right? Sometimes normal force isn't enough to keep up with the gravitational force, and things start to bend and break and collapse. But in general, as long as it's stationary, these two numbers should be the same as each other. And then I just drew a picture here. Well, the car is coasting, but is the car going to keep going the same speed the whole time for forever? Well, no. Eventually it's going to slow down because there was some air resistance. There was some friction of the tires. And so if I were to ask you what the net force in the x direction is, you might say 3,000 newtons. How did I come up with that? Well, in the x direction, which is this dimension right here, we have some air resistance, we have some friction, but since they're both pulling backwards, I just added them. I said we have some friction, we have some air resistance. Let's just add these numbers, there's 3,000. What would be the case, though, if I asked you what the net force was in the y direction? The answer is 0. Because really, this is pulling up with, say, positive, but this is coming down with negative. They balance each other, don't they? Like they'll be equivalent to each other. So in this direction here, we have a net force slowing us down. I could even make it negative, perhaps, just to indicate that it's pulling us backwards. But in the y dimension, there's no net force. So with my remaining 20 minutes then, if you kind of get the concept here, I want to do 3 examples just to kind of show you how this looks. So here's example number 1. I just need to grab my calculator because I'm going to need that in a second. So let's try this example. Say there's 2 dogs, and the 2 dogs are going to pull a sled across a flat, snowy surface. So if I wanted to draw a free body diagram, don't worry about drawing a picture, just draw a box. So here's a box. This box is a sled. Okay, and there's a dog that's pulling it 200 newtons forward. So I could say that this way is forwards, and that is 200 newtons. Perfect. Dog A is pulling the sled. Dog B is also pulling the sled. But it's only pulling at 150 newtons. Can you guys see that, how dog B is only 150 newtons? Well, to draw this kind of appropriately, I might draw this probably only about that far and say 150 newtons, because proportionally, the first dog pulled greater than the second one, right? Like 75% is how much the second dog pulled compared to the first one. See, we usually draw the lines kind of to scale to indicate that both of these dogs right here were pulling, let's call that one forward. But there's friction. Friction doesn't speed you up. Friction slows you down, right? So it'd be appropriate to draw a small little line. That's probably still even too big. Let's do a better job, Chris. Let's do better here. If the friction force is 60, that should be even smaller still. So let's draw like a small little line here and call that 60 newtons. And it's pulling in the backwards direction. So this is a pretty easy question. Well, actually, I missed one more thing. It says actually the driver is also trying to slow down the sled by using a force of 100 newtons. So if he's trying to slow down the sled, wouldn't that make sense that you're kind of pulling backwards as well? Let's make that 100 newtons. So really, what's happening here? 2 dogs are trying to pull you forward. Friction is trying to prevent that. And the brakes are also trying to prevent that. My question is, what is the net force? Now, we always have to do net force in 2 different dimensions. Let's actually do the y dimension first. How much net force is there up and down? 0, yeah. Because either he'd be floating or sinking into the ground. And I don't think either of those are happening, because really, there is a gravity pulling him down, and there is a normal force holding him up. But I don't really care about these forces because they're going to be equal to each other. So that was kind of a silly question, but I thought I'd do it anyways. What about the net force in the x direction? Yeah, because what did you do? You took 200 and you added it to 150, but then you subtracted 100 and subtracted 60, because these ones are kind of going in the positive direction and these ones are opposing it. So 200 minus 100 is 100. Add 150 makes back to 250 minus 90, yeah, 190 newtons. So that's your net force. And I would add one more thing, though. I would put an F afterwards, just to indicate that you're still going forward, though. What would it mean if your net force was backwards? It means you're either slowing down or you're actually going backwards. Right? Like if your net force was backwards, it means it's either trying to slow you down or you actually are going that direction, one of the two. Okay, that was kind of my first example, real entry-level one. All you literally had to do was add and subtract numbers. Do you guys have any questions on that one so far? Okay, let's try one more. Let's try another example here. Let's say a car gets stuck in a snowdrift. And we got a couple people who are going to help pull it out. This guy right here is going to pull 15 degrees north of east. And this guy right here is going to pull 20 degrees south of east. And so they've each attached a rope to themselves, and they're pulling at different angles right here. And friction is kind of pulling you backwards. Well, to solve this one's a little bit more complicated. We need to make probably a vector diagram. First, though, I'm going to make a free body diagram. Honestly, this picture right here is what's known as the free body diagram. I already have one there, an FBD, a free body diagram. We've got a frictional force pulling you backwards, but on its edges, these guys are getting pulled forward. So that's a free body diagram. But I need to break this up now into the X and Y components, and this is going to be really similar to what we did in kinematics. I want to focus on this first triangle right here. I'm going to draw it in purple, apparently, since that's what color I'm on. I'm going to take this triangle, and I'm just going to draw it over here. I'm going to draw a vector diagram. For those of you who, by the way, did your lab the other day, and maybe you didn't earn marks because of a vector diagram, this is a vector diagram. This right here, not really a vector diagram, that's just a graph. A vector diagram is where you draw a triangle and you have the hypotenuse, you have the X, and the Y portions of it. Here's how this vector diagram would be drawn then. The angle in the corner was 15 degrees. But we know the hypotenuse amount. It actually says in the question that the one person pulls, they're actually pulling along the angle with 75 newtons. So 75 is right there. But just like we did in our kinematics units, some of that is going in the up direction. Some of it is in the sideways direction. It just is actually traveling along the hypotenuse. Hopefully that makes sense, right? The idea that the hypotenuse is where it's actually going, but we can break it up into some of it is going in up and some of it is going over. How can I calculate this force in the Y and X direction? SOHCAHTOA. Let me first give you the answer, then let's talk about how we did that. This is 75 sine 15 degrees. This one is 75 cos 15 degrees. Hopefully your numeracy skills are getting a little better and you're kind of like, yeah, I get this. But let's say you're not. That's fine. Let's go over it. Here's how I did that. I'll use another color just to differentiate. We know that this side is the hypotenuse, this side's the opposite, that side's the adjacent in a nice right angle triangle. It's right angled though because X and Y are always perpendicular to each other. Right? Well, we could write out that sine of theta is opposite over hypotenuse because that's the SO part of SOHCAHTOA. But let's fill in some more numbers. The sine, well, we know the angle was 15. The opposite was the force that was the Y portion of the force. And we know the hypotenuse because the hypotenuse was 75. Well, we're being asked to solve for Fy, so don't you just times the 75 to the other side? Wouldn't that just make it 75 sine 15, which is what I wrote there? So if you're getting a little better at this, we're going to keep using those same concepts through this next unit, but I can actually tell you what the X and Y values are going to be. One is 75 sine 15, one is 75 cos 15. I'm just going to erase this because I don't really need that. Let's talk about our second vector. The second vector we need to deal with, let's draw it in blue here, is, well, there wasn't just one person pulling on this car, there were two. There was a person pulling also kind of towards our right, but they kind of pulled down and made this triangle right here. So let me draw another vector triangle. Someone pulled mostly this way, but they pulled a little bit in the downwards direction. So that means that their net was this way. And if I fill out some information, the angle was 20, and this, I believe, was 68. So let's break this up. Why don't we call this one Fx number 2? Let's make this Fy number 2. And why don't I go back up and I'll just label the purple ones. This will be the first one we did. So here's the first triangle we did. Here's the second triangle we did. how can I calculate the different components? Give it a try yourself. Just think about what it is before I tell you. If this one was 75 sine 15 and 75 cos 15, what are these two going to be? Just don't yell it out. Just think it to yourself, just to see whether you know it or not. So this one's also an adjacent. This one is going to be 68 cos 20. And it's going to make this one 68 sine 20. We've done this before. Like, this is literally what we were working on in kinematics, right? The more we do this, the better we're going to get, actually. Okay, let's talk about why this is so important, though. See how this guy's getting pulled slightly up, slightly down, but they're both pulling over? But hang on, we forgot about the force of friction. Friction's pulling us backwards. Let's talk about that now. Let's do our net force now. If I were to ask you to find your net force in the x direction, weren't both of the two vectors pulling forward? So couldn't we say that we should really be adding 68 cos 20, and we should also add 75 cos 15? Shouldn't we add the two x components? That would be this one right here, and this one right here, because aren't they both pulling towards my right? What about friction? What should I do about friction? Subtract it. But then I got to subtract 40 because it was going back the other direction. These guys we're going to add because they were going this way and this way. This one I'm going to subtract because it was preventing me from moving. So let me find that value now. 68 cos 20 plus 75 cos 15. But then I've got to subtract off the 40 for friction. I've got this value here. I've got 96.34. Okay, now we know how much we're getting pulled in the x direction. Right? If I were to kind of draw a picture of it, one guy pulled this way, another guy pulled this way, friction tried to get in the way, and so the remaining leftover bit is 96. But hang on, we're actually not done yet. This is very similar to some of the stuff we did in kinematics. We have to consider our y net as well. We have to consider the y dimension. Because one guy was pulling up and one guy was pulling down, but I don't know that they were exactly the same as each other. Because I believe the one that was pulling up was 75 sine. 75 sine 15. And the guy that was pulling down was 68 sine 20. I should figure out whether there's actually like a little bit of up or down direction to this as well. So I'm going to find those values. 75 sine 15 is 19.41. And 68 sine 20 is 23.25. So I know that both of these vectors right here were trying to pull, ultimately they were trying to pull towards my right. But one guy was pulling up, one guy was pulling down. Was it exactly even? Not quite. The guy that was pulling down kind of won a little bit. So here's what that means. If I were to find my F net and Y, I should be subtracting these numbers from each other. I'm going to take my 23.25 number, and I'm going to subtract my 19.41 number, and I'm going to say that there's a net force of 3.84 newtons down. So there was some force that was going to the right, but some of it was going down. I'm almost done here. We did this, and we have been doing this in the kinematics unit. This is the type of question we have to solve for where the dart hits the ground or for where the rock hits the castle. If we want to find the final resultant force, we got to put it back together. We had a total force in the y direction here of about 94, give or take. But it went slightly down by about 4 units down. What do I actually have to solve for? a squared plus b squared equals c squared. We got to solve for the hypotenuse. Now, I'm kind of running out of time right now, and you guys can probably do this yourself, but this is at its core how you solve a question like this, is you find all of your x direction and figure out the sum of your x direction. You find all of your y direction, find the sum of all your y direction. You put them in a triangle like this, and you use Pythagoras' theorem to find the hypotenuse, because that's how much actual force there was. We could also solve for the angle right here. Because this car that was getting pulled out of the ditch, it wasn't getting pulled straight out, it was getting pulled out on a bit of an angle. To do that, if you do the tan inverse of 4 over 94, that should tell you this angle right there. It's just how far off this was. Yes? Oh, the 94, was it 90? Oh, sorry, it was 96. Thank you. Thank you for asking. Sorry, this number here was 96 to the right. I'm being a little lazy. This was 96. So I guess that was 96. Good catch. Does that make sense, though, as to where it was coming from? I'm sorry, I'm a little running out of time here, so I'm speeding up a little bit on things. Anybody else have questions on kind of the big picture of how we solved that? Because I got one more example I want to try. I've got 5 minutes left here. Anybody have questions on this one as to how we solved it? Okay, here's the last one. I'm not going to solve this one for you. I'm actually going to show you how to solve it. I'm actually going to assign this. I'd like you guys to try this on your own time a little bit later today or tomorrow morning or something. But I want to present this scenario right here and describe this one. Imagine that you have a sign. And this sign right here is being held up by these two different ropes. Now let's just discuss for a second how this is working here. Let's say that we cut this rope right here. Wouldn't that cause the sign to kind of swing out to the side a little bit? But because of the presence of the second rope, it kind of sticks out to the side here a bit. Now, we technically have a free body diagram kind of already drawn minus one more force. What force is not currently being drawn in this free body diagram? Gravity, yeah. Because gravity wants to pull the sign down in the first place. And so what we really have is three forces. We have a tension, kind of pulling at a bit of an angle here. We have a second tension pulling directly sideways, and gravity's pulling us down. Now, I want to describe to you how you're going to solve this, but your goal, I want you guys to try this one. Okay. See how this force right here is only in the x direction? But this one right here is only in the y direction. Let's talk about the angled tension force. Let's say that I drew a triangle out of it. Maybe I could draw a triangle like this. The tension that we're actually looking for is the one on the hypotenuse. But in a way, this tension, there's some in the y, and there's some in the x. Is this sign moving? I don't think so. I mean, wouldn't it make sense that it is suspended by these two ropes? Here's what that means, and this is where I'm going to end our class here. Let's say that I know that the force of gravity in the y direction is 245 newtons, because the question tells me it's 245 newtons. I can use just that number alone to solve for so many things. Just watch this part here. If this vector going down is 245, then this vector going up better also be 245. Because wouldn't they have to be equivalent to each other? Otherwise, either the rope is breaking or the sign is floating. Those are the two possibilities, right? Either the rope breaks because this is too big, the rope has slack because it's floating because this is too big, or it just hangs there because these two things are the same as each other. Well, as soon as I know that this side right here is 245, I can use trigonometry, and I know that this angle right here is 35 degrees because they add up to 90. And as soon as I know one side of a triangle, I should be able to find the other two sides of the triangle using SOHCAHTOA. Then, one last color, and then I'm done here. Well, however much this sign is pulling this way, let's just say it's 100. Well, then this one right here would also have to be pulling 100, right? Because if it's suspended, it means that this rope right here and the x portion of this rope right here, they should be equivalent. Otherwise, the sign is either going to our left or to our right. And so what's kind of cool about this question here is with just one number and an angle, we can actually use this number to find this y, this y and an angle and SOHCAHTOA gives us both the other two sides of the triangle, and whatever this side right here is that one there. So here's my goal for you guys since I'm about done for the day. I've walked you through how to solve it. I want to begin tomorrow's class, and I want you guys to try this on your own. See that you can solve this, because there's not really anything that's that brand new. We've already discussed vectors. We're just using them in a different way now.